Hello. In this tutorial, we're going to be discussing how to write and implement a linked list data structure. So to begin with, let's actually add that. Let's create a new Java class I'll call list. And into this class, we need to manage another data structure that's going to be a particular node in our linked list. So a linked list is constructed by chaining nodes together with references to the next element in the list, and we could implement a list with an array and then grow that array like we've done earlier this semester. But right now I want to implement this using a data structure of a node, and we're going to define that node here inside of our list class. So the first thing to do is inside of the list we're going to create a private class node. And you can actually define a class within another class, and the reason I'm going to do that within the list class is because I want this node to be private. I don't want anyone outside of the list to be making use of it. So it's going to contain two elements, a data element and a next element. Okay, now within this class I'd also like to define a constructor that takes in data and also a node next, and very simply it's just going to say that the data is equal to that d parameter and that next is equal to this n parameter. Last thing I'd like to do is define the toString function. So let's override the toString. And it's just going to return, and you could do this however you'd like. I'm going to choose to put square brackets around my data like so, and draw an arrow indicating that this node is made up of the data plus a reference to, and I'll leave it to the next node to display itself. Alright, real simple class. You could make the data and next private with getters and accessors, or getters and setters there. You could add a little bit more if you'd like to. For our purposes, this simple node class will be sufficient to manage our linked list. Now, the next thing I want to do is focus our attention on the list class itself. So the list class is going to need to maintain a property called listhead, which is of type node, and it's going to be the first thing that the list points to, and thereafter all of these nodes will point to each the next one in line as it goes along. Okay, so we'll need this list head, and we're going to need to be very careful in our programs to not move this or modify it unintentionally. Otherwise we're going to lose all of our data, because the rule in Java is if I don't have a reference to an object, then the object can get collected by the garbage collector and it just doesn't exist in memory. Let's create a simple constructor for our list, and we're ready to go then. Inside of main we could create a list, let's call it data is equal to a new list, and we're all ready to get going with this then. We can't do anything with this data list yet inside of main, so let's return to the list class itself and give the user the ability to insert a value into it. So let's create a public function. It's not going to return anything. We'll call it insert, so it's public void insert, and you give me a value, and I'm going to create a new node that I'll pass the value, and I want to add this new node into the beginning of my list. So creating the new node and placing that value into the data will fill up that data field. The second parameter to my constructor of the node is going to be the list head, and that's going to make sure that this new node that I create is filled with data and points to the beginning of the list that already exists. And then the only thing I need to do is set listhead to be equal to this new node I just created. Now listhead will always point to the beginning of my list, and since I create this new node and have it point to the beginning of the list and have listhead point to this new node, this is going to insert a new value, a new node, into the beginning of my list. Okay, what if we wanted to add something to the end of the list? Let's create a new insert to end function that takes in a value. And the work here is going to be a little bit more complicated in that I want to repeatedly go along throughout the list, and until I get to the end I want to keep looking. So let's start off this variable current, which is a node, and I'm going to point it to the beginning of the list, and while current next is not equal to null, meaning there's still another node out there, I'm going to move current along in the list and move it down to the next position. So this is going to get me to the end of the list, and I can just simply say now current next is equal to a new node, value and null. This will place a new node at the end of the list because I start out at the beginning. I repeatedly loop until I'm at the last node. This test here is going to get me to where current is a node and it's not at the end. I mean, it's at the end of the list, but we haven't gone to null. So current will be pointing to the last node in the list. Now, if current next is assigned a new node, that's going to tack on this new node to the end of the list and place the value into that data portion and just have the next pointer pointing to null. And this is almost perfect, except what happens if the list is initially empty? If we were to run this right now and there's nothing in the list, then current points to list head, and list head is initialized to null, so null.next is going to throw a null reference exception, and we'll never be able to actually add anything. So the first thing I need to do in this code is to actually say, if list head is equal to null, that means there's nothing in my list, then it's going to be that list head is a new node on this value. So that's going to handle that case where there's nothing in my list to begin with. So start it off by making list head point to that first new node that we create. So if there's nothing in the list, make the list point to this single new node that I'm creating. Otherwise, I know that there's got to be something in the list, so move until I get to the last node and then tack on this new node to the end of the list. And that'll do it for inserting to the end. Now we have the ability to insert, and if we go into main, we could certainly say something to the effect of data.insert on, let's say, the value 13, and this will work. We could even say data.insert to end and place the value, let's say 89, at the end of the list, but we'd like to be able to display this list so we can see what's going on. So let's override the toString for the list class itself. So we'll do @override public string toString, and let's code up the toString function for our list. We'll have a result that I'll initialize to the empty string to begin with, and you'll notice a pattern here. I'm going to use the current and move it along in a while loop. And the reason I don't modify list head is that if I were to change list head, then there would be nothing pointing to the beginning of my list, and I would lose all of that, and the garbage collector would come along and deallocate it. So we've got current pointing to the beginning, and while current is not equal to null, meaning there's still something in my list, I want to add on to this result and say result plus equal current.toString. And since we wrote the toString function for our list node class right here, then it's going to automatically take care of displaying the current node. Once we've dealt with current, we can just set current to current.next, and that's going to move current further along in my linked list there. Once we get out of this while loop, I know that I've displayed all of the nodes, so I'm just going to return result plus, and I'm going to use the double pipes here to indicate that that's the null, that's the end of my list. You could certainly leave this off, and that's perfectly fine, but just as a stylistic point, I'm going to make sure that I realize that the list is pointing to nothing at the end, or you could write something like null, like this if you wanted to. Okay, so the toString function starts out with an empty string, and it puts current to the beginning of the list, And so long as current isn't pointing to nothing, then we're just going to tack on the current string to our result and keep adding that to the end of the string. And eventually we're going to move along the list here and get to the end, in which case we'll return the result plus null. So let's go check out back here in main. Let's say system out println data, and that's all it'll take to display the data structure out to us. We're going to then insert 13 and print data, and then insert 89 to end and print data. Notice the values are going to go to the beginning unless we use the insert to end function. So if we run this, we see that we get null to begin with. That means there's nothing in the list. And then we added 13, and then we added 89 to the end. We could add other values. Let's do an insert on 42 and print out the linked list. And 42 should be at the beginning since we're always adding to the front. Continue this on by adding, let's say, the value 9. And the value, let's have a duplicate here. Let's put in 13 again. And if we run now, we'll see that we get 13 added first, and then we added 89 to the end, and then we added 42, and then we added 9, and then we added 13. So we're always adding to the front there. Let's add something like 900 to the end. And one more system out println just to show that the insert to end is working no matter how large our list is. So there's our 900 that we just added. And you can see that the list is growing quite nicely as we add these values. Let's return back to our list class now and add some capability to it. What if we wanted to calculate how long the list was, how many values were in the list? Let's create a public function called length that's going to return to us an integer. And we could maintain an integer within the linked list class called count, and every time I insert something I could increment count, and every time I would delete something I could decrement count, and then I could just return the value of that count here. That's one approach, and it would be very fast to do that because this would be a constant function, meaning there's just one instruction to perform. But another approach, and I want to take this one here just to demonstrate this pattern again of traversing the linked list, is to go across the list and move this pointer, this temporary pointer current, from the beginning all the way to the end. And when we get to the end, if we add one every time for each node that I visit, then at the end this result is going to be how many nodes are in the list. So we'll have our current that's equal to list head, and I'm going to have my while loop again. So while current is not equal to null, I'm going to increment my result, meaning I have seen a node now, and then I'm going to set current to current next, and that's going to move me to the next node in my linked list and advance on. And then I just need to return result. Simple function. Every time I see a node, I'm going to increment and then just move on to the next node, and I'm going to keep doing that until I reach the end of the list. Quite easy. So back here in main, we could say something to the effect of that we have length of the list is plus data dot the length function needs to get refreshed here. So back here, data dot length, and there it's finally showing up. And if we run, we'll get that the length of the list is 6. We have 1, 2, 3, 4, 5, and 6 values, sure enough. In addition to calculating the total length, perhaps I want to find the largest value. So let's do a public int max function that is going to return to me the maximum value that is in this list. Okay, so we'll have a result here. And the trouble is, if the list head is equal to null, that means there's nothing in my list. So I'm going to, one could argue, oh, let's just return -1 to say that that's the largest value in the list. Well, the trouble is maybe all of our numbers are negative, in which case -1 would indeed be a correct value for the maximum. So I'm going to throw a new exception, actually. This is a perfect example of when exceptions are really required because there's no other way around this to say that there are no values in the list. And rather than get complicated and create my own definition for a new exception type, I'm just going to use the base exception class and pass it this message, no values in the list. Now it's complaining here because I need to report that this function can throw an exception. And once I do that, all is well. And I can then proceed right here knowing that if I've made it to this point, I know that my list head at least points to something, and I can then begin that work of traversing the entire list and verifying the largest value. So the result is going to be initialized to the first value in the list because current is pointing to list head now, and I'm going to pull the data out of that and store that in result. So long as I'm not at the end of my list, I want to say that if the current data is greater than result, meaning I have visited a node that has a new larger value, then the result is going to be equal to current data. And then move current to the next node in the list. When all's said and done, I can just return result. And this is going to give me my maximum value. So here, at the beginning of this, if the list contains no nodes, I need to throw a new exception. Otherwise, I'm going to initialize my current to be a reference to the beginning of the list, and I'm going to set my maximum that I think that I have to be the data at that first node. And so long as I'm not at the end of the list, I'm going to see if I have a new maximum at this new node that I'm at, update my result if so, and then move on to the next node and keep doing that until I get to the end of the list, in which case I'll just return the result, which is the maximum. Okay, so let's actually call this max and say that the max value is data.max. Okay, and now I'm going to be able to invoke that function and determine what the largest value is. So let's run this, and it says that the maximum value is 900. There we are. So it found it. It was the largest in the list, and in this case it happens to be the end. It's just to verify that we're not cheating. It's not always going to be the largest value. Let's make sure that we insert something else to the end. In this case, let's say 19, and let's see if it still finds 900. Okay, so we do a search, then we found the max to be 900, and then we're going to insert 19 at the end, and we call max again, and it still finds that the max is 900, which is exactly what we want there. The next thing I'd like to do is add the ability to find the position of or do a search within my list. So let's add that then. What I want to do is take in a value and determine the position of that value. So let's call this function position of, and it takes in a value to find, and it's going to return the integer location of that value that we found. I'm going to initialize my return value. In this case, I want to count this up and start off my current at list head, and while current is not equal to null, again, just common pattern of searching to the end here, I'm going to say that if the current data is equal to this thing that I'm trying to find, I'm going to return I, which is my counter here. Otherwise, if I haven't found the match yet, I'm going to set current to be equal to current next and increment my I. So I'm just incrementing this I every time I move to a new node. This should look very familiar to you. And once I find a match, I'm just going to return the position that I'm at. Well, if I get down here and I left, that meant that current is equal to null and I never found a match, so I'm going to return -1. and this will indicate that the value doesn't exist. Now, -1 is a valid message to return back if the node isn't found, this value isn't found, because the position should start at 0. The first value in the list should be 0, so -1 means that it's not there. If we go here into main, we can search now for the position. So let's look for the position of the value 42 is data.position of 42. And let's look for the value 89. And let's see this work. If we run this, we get that the position of 42 is 2. Now remember, we started counting at 0, so that's 0, 1, 2. Good, it found it. And the position of 89 is 4. 0, 1, 2, 3, 4. Great. Well, what if we look for something that's not there? Let's look for the value, let's say 1200. And 1200 isn't in our list, so it should return -1 to us. And that's exactly what it does here. The position of 1200 is -1. Great. Well, beyond just searching for the value, what if we wanted to do a search and replace? All right, let's add another method. This is going to be a public void, and it's going to take in a new value and an old value, and it's going to iterate across the list, and every time it finds this match, it's going to replace the data. Okay, we have our pattern again of using this current node and setting it equal to list head to begin with, and while current is not equal to null, I'm going to repeat and say that if the current data is a match to the old value, then current data is equal to this new value. So I'm going to update that node. In either way, whether I found a match or not, I'm going to move along to go to the next position. And that's it for the search and replace. It's actually quite easy, right? We have our repetition to go across the entire list, and every time I find a match on the old value, I'm just going to set the data to be this new value. So if we look at our list here, we've got this will actually do a search and replace on all values. So here I've got these repeats on 13. If I do a data.replace, and the new value is, let's say, 999, and the old value is 13, then everywhere we saw the value 13, we're now going to have the new value 999. So if we run this, what you'll see is that the 13 that we had here is now 999, and the 13 that we had here is now 999. We can do a new quest for the max, and we should see that the maximum is now 999 because we've got this new larger value. 999 is bigger than 900. The last thing I'd like to do is add the ability to remove something out of our list. So far we have the ability to insert and insert to the end. We can display the list. We can figure out how long it is. We can do a search on the maximum. We can find a particular value and return its position. And we can do a search and replace on a particular value. But let's now do a search and delete on a value. This is going to be a public void. I'm going to call it delete. And you're going to pass to me an integer value that you want me to remove. Now this is going to be a little bit tricky in that I'm going to have to do a little bit of pointer manipulation and look ahead in the list. But to begin with, if my list head is equal to null, what do we know about our list? The list is empty, so I can simply return. Now maybe you want to throw an exception here to say you tried to delete a value from an empty list, but if you tell me to delete something and the list is already empty, I'm just going to say, okay, fine, it's not there, I'm done, I don't have any work to do. The other thing I need to consider is I need to do my common pattern of creating my current and setting that to list head. And while current, now this is where it gets interesting, I'm going to say while current next is not equal to null, because I always want to look one ahead. I'm at a particular node, I want to look to the next node and I want to compare that because I'm going to have to move a pointer around that next node. So if the current next data is equal to this thing that I want to delete, I'm saying I'm at a node, I want to go to the next node, and then I want to look at its data. And is that data in the next node in my list equal to this thing that I want to delete? If that's the case, I want to set what I'm pointing to coming out of my node, we call this current next, to current next next. And what it'll do is it'll bypass my next node and it'll just point the arrow around that node. Okay? Otherwise, if I haven't found something to delete, I'm just going to set current equal to current next and advance on to the next node. Now this will work, except it won't actually delete the first node. If we find a match and this thing that I'm trying to delete is in the first node or list head, then it's going to skip over that and it's not going to work. So we need to add, if list head data is equal to delete, then I want to actually move list head to be list head next. I want to move it along. Now earlier in this tutorial I said we had to be very careful in not manipulating list head, and all throughout we've used this temporary current variable to advance on throughout the list. This is a situation where in fact we do want to manipulate list head. If the first node in the list is a match to what I'm trying to delete, I need to make list head point to the next node in the series and not manipulate a current copy of it, because this would just, if I were to move current, it's just going to move a copy. Okay, now let's look into this in more depth and see what's going on here. I'm at a current value and I want to say that is the next node's data in the list a match, and if so, set my pointer that's coming out of me to be equal to the pointer or the node beyond this thing that I'm trying to delete. What this will mean is that current next, nothing is pointing to that next node in the list, and the garbage collector will come along and remove it. I need this else clause here. If I were just to say, if you find a match, then delete it, and then make current go to current next, I would then be skipping over. In the case where I did a deletion, I would have already moved current next to current next next, and then I would move it again, and I would effectively be skipping over the values. So if I had two numbers that I was trying to delete, it would delete the first one, it wouldn't delete the next one. So I'll leave that to you to remove this else and see what happens if you had put in all values of 7 into your linked list, maybe 10 different values of 7, and then run delete on 7, and you'll notice that it's only deleting half of them, not all of them. But if you have your else clause here, it will go through and actually delete them all. So finally, let's go here into main and do a deletion. Let's do data.delete on, let's delete the value of 42 and see what we get. Okay, if we run this, what you'll see is here we had 1, 2, 3, 4, 5, 6, 7 different values, and then we called delete on 42, and now we only have 6 values. It's gone. All right, let's do this again and delete. And this time, let's delete the value 999, and that will demonstrate that we're able to delete correctly the first node, and it'll also delete all occurrences, not just the first occurrence. So let's run this, and you'll see that all of the 999s, this one and this one, have been deleted. Okay, in the textbook you've got a slightly different implementation of the delete method. This is a little bit more compact and hopefully easier to follow, but you can look to that other implementation if you'd like to see an alternative to that. As a recap, let's look at what we did with this list. We created a private node that we were able to maintain 2 important fields. We had the data that would actually hold the information, and then we had a reference to the next node. We've got a nice constructor and a toString function. Within the list class itself, we maintain this listhead property that points to a node, and we initialize that to null when we began. With the constructor here, we were able to insert to the beginning and also insert to the end, and this is the first case where we have this pattern of repeatedly going to the next node until we're not at the end. We overrode our toString, and you've got your while loop again, where we're using this current node and advancing it along until we get to null. We were able to calculate the length of our list, again using this while loop structure. We could find out the largest value. We could find the position of a particular value, or in this case the first position, in case there were duplicates. We could do a search and replace on an old value to a new value using this while loop structure. And finally we finished off with the delete function that searched for this value, and anywhere that it found a match, it's going to bypass that node and remove all instances or all occurrences of that value from our list. You can see through main that we can make use of these functions and visualize what's going on in memory with this linked list structure. And that'll do it for this tutorial on how to implement a linked list using nodes and pointers.